Okay, welcome back to Chapter 5 of our Physics 2010. So I was kind of cut off in the middle of the last video because the software I'm using only allows me to do 15-minute videos. So just to wrap up this slide, the concept to understand here is that the velocity, the linear velocity of the ball or whatever the object is traveling in the circular path, its velocity at any given point in time is tangent to the curve. And so if we were to let go of the string or somehow the force keeping it on that circular path were to disappear, the ball would travel in a straight line tangent to the curve. And that is what centripetal means, because the force keeping it on that path is pointing towards the center. It's center pointing, and if it were to go away, the object would fly off in a tangent direction. The centrifugal or centrifugal means center fleeing, but that is not what we're talking about here. So centripetal, not centrifugal. Let's look at an example problem here where we are spinning a ball on a string at in a horizontal path. So we have a mass of 0.150 kilograms. The radius r is equal to 0.600 meters. And the revolutions, it makes 2.00 revolutions per second. So that's its frequency, is 2 revolutions per second. So its period is 1/2, or 0.500 seconds. So we're going to ignore the mass of the string and just consider the ball that's traveling in this horizontal path. We want to know the force that the person must exert on the string to keep the ball following this path. So the first thing we want to do is determine the velocity of the mass of the ball. And so the velocity is 2 pi r, that's the circumference of the circle, divided by the period. How long does it take to travel around the circle? So that's going to be 2 pi times our radius of 0.600 meters, divided by the period, the amount of time it takes to go all the way around, 0.500 seconds. And that should give us 7.54 meters per second is the velocity. Once we know the velocity, we can then find the centripetal acceleration. And we're going to plug that into our Newton's second law of motion. The sum of forces equals mass times centripetal acceleration. And centripetal acceleration is velocity squared over radius. So the mass of the ball is 0.150 kilograms. The velocity we just determined in part, the first part up there, 7.54 meters per second. Don't forget to square that, and then divide by the radius of 0.600 meters. So 0.150 times 7.54 squared divided by 0.600 should give us 14.2 newtons. That is the force in the string when this ball is spun around in a circle at this speed. Okay, so when we look at a ball spinning in a horizontal path like this, gravity is always affecting the ball the same way with relationship to the tension force, regardless of where on the path that ball is. If the ball was over here, gravity would still be acting down, and tension would still be pulling it in towards the center of the path. Let's look at an example where we're spinning it in a vertical circle. In this particular instance, the relationship between gravity and the tension in the string changes depending on where in the path that ball is located. At the bottom of the path, gravity is pulling it down, and the tension in the string is pulling it up. They're acting in opposite directions. When the ball is at the top of the circle, gravity is still pulling it down, but now the tension in the string is also pulling it down. So if we were to investigate this type of situation, we can really only look at these 2 points. I mean, we could investigate other points, but mathematically it would be a lot more complicated. These are the 2 simplest points to look at. So we'll investigate what's going on here at the top and what's going on down here at the bottom. Those are going to be the 2 extreme values where the 2 forces are opposed to each other and when they're acting with each other. So at the top of the circle, if we look at the forces here, they're both acting down. And so if we were to sum the forces at the top, the sum of the forces is equal to m times the centripetal acceleration. So what are the 2 forces at work here? Well, we've got the weight, mg, and it's going in the same direction. I'll just make them both positive in this case. It doesn't really matter if they're positive or negative so long as they have the same sign. So I'll make them both positive to keep things a little simpler. So the weight, mg, plus, we'll call it ft1, the tension force in the string at the top, which we are labeling condition 1. So those 2 forces combined have to keep the ball in this circular pattern, which is equal to m times the centripetal acceleration. So it's m times v squared over r. Okay, so I made a little scribble over here accidentally. Don't pay any attention to that. But what I wanted to say here is if you've ever spun something vertically like this, you know it has to be a minimum velocity. If you're not spinning it fast enough, if the centripetal acceleration isn't great enough, when the ball gets to the top, gravity will take control and will just sort of fall down. So we need to make sure that the velocity is great enough to keep this ball spinning in its circular path. So essentially we need to solve this equation for velocity to figure out how fast do we need to keep it going so that these forces will kind of balance each other out and the ball will continue to follow this circular path. So if it's the bare minimum velocity here, the gravity pulling the ball down and the centripetal acceleration will oppose each other, and we will actually have 0 tension in the string. That's going to be like the bare minimum amount of force to balance this out. So imagine we're spinning it just barely fast enough to keep it in the circular path. When it reaches the top of the string, gravity is going to be doing all the work for us, and we actually don't need any tension from the string. So that just becomes 0. And so we've got mg is equal to mv squared over r. Okay, well, these 2 terms have m in it. We can cancel that out. So we've got g equals velocity squared over r. So if we want to solve for velocity, multiply both sides by r. So now we've got gr is equal to v squared, and then V is equal to the square root of GR. Okay, so let's finish this up with V equals the square root of GR. G is the acceleration due to gravity, 9.80 meters per second squared. And our radius in this problem is 1.10 meters. And so the square root of 9.8 times 1.1 gives us 3.28 meters per second. That's the velocity required to keep the ball spinning in the circular pattern at the top. Now let's consider the bottom. Okay, so the problem statement here tells us to consider at the bottom, for some reason, that the velocity at the bottom is equal to 2 times the minimum velocity, which was the velocity at the top. So if I go back here and look at what we found, 3.28. So at the velocity at the top was 3.28 meters per second squared, and so the velocity at the bottom is going to be double that. It's going to be, what would that be, 6.56 meters per second. I don't know why the example problem doubles the velocity at the bottom, but it does. So what's the big difference between the bottom and the top? Well, the biggest difference is the fact that the forces are now opposing each other. Before, they were acting in the same direction, and in fact, the way the problem statement was worded, we wanted to know the minimum velocity required to keep it in this path. If the velocity gets too slow, the tension in the string goes away and the ball falls out of its orbital path. So we want to know the point where this was equal to 0. Down here, we've doubled the velocity, and now we want to know there definitely is going to be a tension in the string because it has double the velocity and has to keep up the weight. So what is that force going to be? We need to solve for Ft2. So if we apply Newton's second law of motion, F equals ma, our acceleration in this case is centripetal, so it's mass times velocity squared over r. So our forces are equal to mg going in the downward direction, Ft2 in the upward direction, and that is equal to mv squared over r. It should have been a lowercase r. So if this is what we want to know, let's just solve for Ft2. It's going to be equal to mg plus mv squared over r. So that's going to be equal to our mass of 0.150 kilograms times gravity is 9.80 meters per second squared plus 0.150 kilograms times 6.56 meters per second, which is our velocity for part B of this question, squared divided by the radius of 1.10 meters. So if we solve that, we get Ft2, not Tt2, Ft2 is equal to 7.35 newtons, is the force in the string at the bottom of this path. So that takes me pretty close to my 15-minute limit, so we'll stop here and resume with the next video.